From scenario modeling of subduction events to interpreting data, numerical modeling has been crucial for studying tsunami generation by offshore earthquakes. To best interpret this data, we rely on computer simulations that closely represent the real world. I'm Lauren Abrahams, and today I will be presenting our research on the comparison of techniques for coupled earthquake and tsunami modeling. Many current numerical models utilize one-way coupling using an earthquake simulation to inform a separate tsunami simulation. In these modeling techniques, intentional simplifying assumptions are made to model how earthquake generates tsunamis. However, some of these governing assumptions can limit the modeling technique's applicability. For example, some modelers use a static displacement from the earthquake simulation as an initial condition in a separate shallow water tsunami simulation. This technique is assuming the tsunami propagation is negligible over the earthquake duration, and therefore the earthquake can be modeled as instantaneous. For longer duration sources, other modelers follow time-dependent approaches, using seafloor velocity from an earthquake simulation to act as a forcing term in a separate tsunami simulation. In this third technique, an earthquake simulation is run with an underlying earth and overlying ocean, coupled with an elastic acoustic boundary. The sea surface velocity is then recorded and used as a forcing term in a separate tsunami simulation. The third technique appears similar to the second technique, as it also utilizes time-dependent forcing. However, the third technique accounts for accurate acoustic wave generation. Even though all three techniques use a shallow water tsunami simulation with an incompressible ocean, and therefore cannot generate acoustic waves in the tsunami simulation, the third technique accounts for acoustic wave generation in the earthquake simulation. Here, an earthquake simulation models the seismic waves in the earth and acoustic waves in the ocean without gravity. In the earthquake simulation, the sea surface will record the acoustic wave generation and the static sea surface deformation formed due to the lack of gravity. When the sea surface velocity is then used as a forcing in the tsunami simulation, there is a superposition of the earthquake and tsunami solutions, providing the complete wave field. These three techniques use approximations to send information from an earthquake simulation into a separate tsunami simulation. In contrast, the fully coupled technique simultaneously solves for earthquake rupture and ocean response all in one model, creating a more realistic model of Earth-ocean interactions. This method was developed in 2D by Saito and Dunham 2015, inspired by a similar technique by Madea and Furumura 2013. The fully coupled method has recently been incorporated into the earthquake software Saito, allowing for 3D modeling. Through a newly implemented free boundary surface condition, gravity is incorporated into the model, allowing for seismic wave generation in the earth, acoustic wave generation in the ocean, and tsunami wave generation due to gravity acting as a restoring force. In this study, we consider how long-duration earthquakes and the generation of ocean acoustic waves impact the numerical modeled data during tsunami generation and propagation. We want to examine how the assumptions affect the model data and under what conditions each model technique can be used. For the earthquake simulation, we will use a no-gravity 3D simulation produced from Saito to inform the tsunami simulation, either with initial conditions or forcing. The tsunami simulation used will be a 2D depth-integrated linear shallow water solver. To compare the techniques, we created a source on the seafloor that's a Gaussian in space and time. Here we are showing a center slice from the previous slide of the velocity profile on the seafloor on a space-time plot. The size of the source and how fast the source lasts is controlled by the source width, sigma r, and source duration, sigma t. A short duration source will cause a quick impulse, allowing for the generation of acoustic waves, whereas a long duration source will allow for the tsunami waves to propagate while the seafloor is still deforming. For both velocity profiles, the final seafloor displacement is identical. We can quantify these effects through non-dimensional parameters. First, for a shallow water solver, the source width needs to be long compared to the ocean depth, h. If the source width is small compared to the ocean depth, it violates the shallow water approximations, and we can expect the filtering of short wavelengths as identified by Kajira 1963. Second, we can examine if the tsunami will propagate over the source duration by comparing the source velocity and tsunami wave speed. Last, we can examine if acoustic waves will be significant. Just to recap, we have a velocity function source that is a Gaussian in space and time. This source is applied to an earthquake simulation through a velocity boundary on the sea floor. In the earthquake simulation, there is no gravity as the restoring force. Therefore, a permanent deformation forms on the sea surface. Information is then passed from an earthquake simulation to the tsunami simulation. For the first method, the seafloor displacement is passed as an initial condition. In the second method, the seafloor time-dependent velocity is passed as a forcing term into the tsunami simulation. In the third method, the sea surface velocity is passed as a time-dependent forcing in the tsunami simulation. These three methods use two-step approaches, utilizing both an earthquake simulation and a tsunami simulation. This differs from the fully coupled method, which models the seafloor deformation and ocean response with gravity, allowing for the tsunami waves to generate and propagate all in one model. Research is always ongoing, and during AGU, progress has been made to the study. Therefore, we updated the slides to showcase the new results. For this first example, we show a problem in the shallow water limit. Based on scaling, we expect the tsunami will propagate over the source duration. Therefore, we anticipate method 1 will incorrectly model the tsunami. Here's the results from the first modeling technique. In the one-way coupled approaches, we have run the earthquake simulation with an ocean without gravity. In method 1, we use the final seafloor displacement from the earthquake simulation as an initial condition in the tsunami simulation. On the left shows a space-time plot showing the sea surface displacement from the tsunami generation and propagation in the tsunami simulation, with the tsunami moving out at the tsunami wave speed. We offset methods 1's results by 1,700 seconds to make it easy to compare to other methods, because in other methods, the tsunami is not generated instantaneously. In method 2, we use the seafloor velocity from the earthquake simulation as a time-dependent forcing in the tsunami simulation. On the right shows the sea surface displacement from the tsunami simulation. Clear differences are seen when we compare the static technique to a time-dependent technique, with method 1 overestimating the amplitude by a factor of 20 and extremely underestimating the tsunami's period. Comparing method 2 and method 3, we see good agreement as both are time-dependent approaches that capture the tsunami propagation over the source duration. The three time-dependent approaches are in good agreement with each other. This is due to the fact that the tsunami will propagate during the rupture duration, so the static initial condition does not capture this effect. In addition, no acoustic waves are excited. Therefore, method 2 matches well with method 3 and method 4. The second example is also within the shallow water limit. Based on the scaling relations, we can anticipate that the tsunami will not propagate over the source duration, but acoustic waves will be significant. Therefore, we anticipate method 3 and 4 will differ from method 1 and 2, as method 3 and 4 capture the full wave field, including acoustic waves. Based on the scaling relations, we found the tsunami did not propagate over the source duration. This is in good agreement when we compare method 1 that uses a static initial condition and method 2 that uses a time-dependent forcing. Method 1 and 2 are in good agreement with each other. However, when we compare method 3, we can see that the results vastly differ from method 1 and 2. Here we expect acoustic waves to be significant based on scaling. And method 3 is able to model the complete wave field. Method 2 does not account for acoustic wave generation, therefore misses these waves. Method 4, the fully coupled method, incorporates gravity through the free surface. We consider this model to be ground truth, as it models the acoustic waves generated in the ocean and tsunami wave generation and propagation all in one model. Both method 3 and method 4 show excellent agreement to each other because they both capture the full wave field. Overall, method 1 and 2, a static and time-dependent method, captures the tsunami wave well because it does not propagate during the source duration. But method 1 and 2 do not model acoustic wave generation, as the linear shallow water tsunami solver does not incorporate compressibility effects. Although here method 3 also uses the same linear shallow water tsunami solver to model tsunami propagation, method 3 incorporates the full wave field. In method 3, the sea surface in the tsunami simulation will record the acoustic wave generation and the static sea surface deformation formed due to the lack of gravity. When the sea surface velocity is then used as a forcing in the tsunami simulation, there is a superposition of the earthquake and tsunami solutions, providing the complete wave field. Similar to the previous example, acoustic waves will be significant. In addition, this third example violates the shallow water limit, which will be noticeable in the results. Method 1 and 2 are in good agreement to each other when both use seafloor information as either an initial condition or forcing. Method 1 uses final seafloor displacement as an initial condition in the tsunami simulation. Method 2 uses time-dependent seafloor velocity as forcing in the tsunami simulation. However, neither of these solutions is actually correct, as we show next. An alternate method for method 1 is using the final sea surface displacement from a no-gravity earthquake simulation as an initial condition in the tsunami simulation instead of the final sea floor displacement. Without gravity, there is a permanent sea surface deformation. In this scenario, the source width is small compared to the ocean depth. The short wavelength components are filtered out on the sea surface. However, on the seafloor, these short wavelengths are significant, creating additional uplift when passed to a tsunami simulation. Here we compare method 3 that uses sea surface velocity as forcing. In this method, it allows for the superposition of the earthquake and tsunami solutions, accurately accounting for acoustic wave generation. Based on scaling, we do expect acoustic waves to be significant, which are prominent in method 3. Here we compare the previous method with method 4, the fully coupled method. Method 4 is considered ground truth to which the other approximate methods can be compared. Looking closely, we see differences in the tsunami component of method 3 and 4. The tsunami in method 3 propagates faster than in method 4. This is because the tsunami is not entirely in the shallow water limit, so its propagation involves non-hydrostatic effects and hence dispersion. Method 4 captures dispersion, differing from method 3 that utilizes a non-dispersive shallow water solver. If instead a Bouskinesque solver was used instead of a non-dispersive shallow water solver, we suspect method 3 and 4 would be in better agreement. In this example, we are no longer in the shallow water limit, causing 1. Short wavelengths to be filtered out, and 2. Dispersive effects to occur. Method 2 does not account for the filtering of short wavelengths, and because we choose a non-dispersive shallow water solver, method 3 misses these dispersive effects. Method 3 and 4 do capture the acoustic wave generation, which are missed in method 1 and 2. In the study, we show preliminary results of a comparison of 4 3D numerical modeling techniques for tsunami generation to understand under what conditions the assumptions made in each modeling technique hold. Specifically, we examine the effects from a long-duration source and acoustic wave generation. We use non-dimensional scaling parameters to justify when each of the techniques' model assumptions hold, finding that method 1 is valid for short-duration sources. Method 2 needs the simulation to be in the shallow water limit, but is valid for both short and long-duration sources. Method 3 and Method 4 are valid for both short and long-duration sources, and in addition, will capture generation of acoustic waves. Understanding under what conditions each method's modeling assumptions hold will lead to better modeling of earthquake-driven tsunami generation, driving more accurate assumptions of potential future hazard, and furthering the development of tsunami early warning. Thank you.